Welcome to the OI Field Tech Seminars. For those of you who don't know me, my name is Luciano Floridi, and I'm the Professor of Philosophy and Ethics of Information here at the Oxford Internet Institute, OII. It is my pleasure to introduce today Professor Chen, and I will tell you a little bit more about him in a moment. But first, a few words about the Field Tech series. The Field Tech is Philosophy and Technology series. It is not Philosophy of Technology, which means that we do not assume that philosophy has necessarily something to say to technology and not vice versa. We expect two ways of interaction between technological innovation on the one hand and philosophical thinking on the other. So basically the two things on the same plane. The series is organized by the OII and by the philosophy faculty in collaboration. It is one of the first cases of collaboration of the philosophy faculty and the OII. So I'm very grateful to both institutions for what they've done for us. The project is quite simple. We meet once every fortnight during term time on Thursday. And the opportunity is to have great speakers, more on today's great speaker in a moment, to have lively interaction. So the format is roughly half an hour talk and another half an hour discussion Q&A. The rest of the program, before I introduce today's speaker, we'll see two more speakers. One in 2 weeks will be Karen Melham, who will be talking about the nature of dynamic consent, and then we will close the term with Professor John Agar from UCL, who will be talking on perspectives and problems of a tool for thinking about modern science. It is an attempt to look at modern science from an STS perspective. About today, Chen is actually from around the corner, is a local, is the Professor of Visualization at the OERC, and he will give us a talk on, had Bell invented visualization, he would have said, now I don't know what he would have said, but I'm pretty sure that if he had said anything, Chen is the right person to interpret whatever he would have said. Now, I don't think I need to add any more. For those of you who need to know more or want to know more about Chen, there is plenty of material on the website where we are hosting the series. With no further ado, Chen, the floor is yours. Thank you.
Thank you very much, Luciana, and thank you for the introduction. So, really would like to talk about the topic of visualization, maybe at a relatively non-technical level, and try to linking with the potential philosophical problems and as well as a psychology, which is also very much connected to the visualization. But of course, and when interesting, the title tells is the Alexander Bell invented telephone, and that also indicated the visualization has a clear connection with the communication, as you probably will agree. And what nice things with communication is a very solid technology and a mathematical theory. What visualization doesn't have is exactly what the communication had. So we're going to talk about that. So of course you're all aware of the data, and whichever one talk about amount of data we have, and we continue to the increase year by year, and according to this chart, at roughly about 2012, we have really close to over 900 and exabytes data available, and according to the internet tells us, and we have this year or last year we had 4 zettabytes, and whether it's correct figure or not, but they are estimated, I guess. And we continue to have a lot of data, and everyone's interested in the issue about big data, how we address that. I hope you like it. It's called there's online. If you type in the keywords big data, you can see a lot of those talks. Some of them are very exciting, and they talk about data. But if you're listen carefully, then you start to wonder, are there any solutions to the big data problem? And we just have to keep growing data, and they talk about. I'm not going to go through that. This is one of relatively more exciting ones. The people tend to use the terminology of 3V in terms of volume, velocity, and the variety. And the other people also introduce varicity and as the fourth V. But if you're looking at the whole framework of the data processing framework, you're including starting from capturing data. So some would really deal with the difficulty for captured data if the data coming up too quickly. And with storage and the transportation problem, they all affect a lot of things. The search and the retrieval, and you've got the data need to be integrated and combined to be a kind of more structured form. And you have a processing, visualization, and the interpretation and understanding. Then also you need to pass on the knowledge to the future, to other colleagues, to other people. So there's a whole sort of process involving in that. And the key things, if you're mapping those whole processes related to what we traditionally call the data information knowledge pipeline, and actually the bottleneck always in the transition from the real world to the data, and from data to information, and from information to knowledge in similar way. Those are the bottleneck. The other day I was giving a talk in the business school, and I said, those are also the business thrived at those bottleneck points. If you have a solution in those bottleneck place, and that usually is the place under the business who can do well. So those are the key things. But naturally to ask a question is, what is data? What is information? What is knowledge? If you look at the definition from Oxford English Dictionary about what is information, essentially says is the facts or knowledge and provided or learned and so on. And there's a various of other definitions. There's the terminology of information actually is coming quite early, and the late 14th century, we already have that word started coming out. So it's not really as new as we think about it, but there's a correct connection with facts and the knowledge. But on the other hand, we also have the mathematical theory about information, which is the Shannon's entropy. And I'm not going into the detail. There's a definition about that is largely concerned with uncertainty. Question whether the definition of information theory, particularly the term information in that particular theory, is the same information we talk about that. There's a more intuitive definition, and nowadays is quite commonly attributed to the Gregory Bateson, although there's a dispute. There's a computer scientist that actually did some research on it and claimed this actually wasn't really Bateson said. But anyway, and he says that information is the difference that makes difference. And I particularly like this particular, the interpretation of what the information means. And people often use ask, how do you say that? So we will say, that's what exactly the newspaper do. And the newspaper is looking for all the things are different, but they're not going to put all the things on the newspaper. So they're going to looking for the things is going to make a difference, put on the newspaper. So there's a first difference, and there's a second difference. Then from processing point of view, there's the first stage of you coming with data, and we know how to compute the first stage of difference. We know how to do the first stage difference, but we can't compute the second stage of difference because we don't really know what is going to make different to you, because you're all there. That can't be computed. So there's the information theory, the mathematical theory Shannon has, is only address the first part of the information about how to compute the data to work out what is the difference. The second part, which is involving social science, psychology, or a variety of aspects which we needed. And that is the interesting part. In fact, most people were concerned about information. So itself is a big topic, and we can probably continue to study that. And I mentioned that's the standard. So there's no good definition for the second part of information. Then on the knowledge side, and unfortunately, the literature such as the English dictionary fails completely, and tells that the knowledge is the information and the skill. So knowledge is information, information is knowledge. kind of a dictionary fundamentally doesn't work when it comes to those things. And I'm sorry, most of you probably work in the philosophy. I took the quote from Keith, and he said that we all agree the knowledge is valuable, but the agreement about knowledge tends to end there. And I'm not sure whether true or not. And what exactly is knowledge, we actually haven't really quite worked out. And in that respect, hopefully some of you will give a better answer than the Keith. Obviously, he's a well-known philosopher. And you may think we actually agree on what is data, which is just bytes in the computer stored on that. But if those data stored on the computer considered to be data, what about olden days people used to sort of writing on the trees and painting on the walls? Are they data? And if I take a photograph of this picture and I'll give it to you, you will agree I'll give you on a USB stick is the data. But why the material recorded by photograph is not data? They store more information than the image itself. So if we generalize the interpretation about the existence of very philosophical questions, those are what being recorded are also data. In other words, the human has been dealing with big data all the time. And if you look around how much data you're actually seeing, not only see 20, 30-ish people, you see the wall, you see the plugs, you see how many doors, and you see how many float ceiling above us, and you see the details of the grain of carpets. But actually, until I say that, you probably say, I never noticed the grain of carpets at all. And so we've been dealing with data all the time. When you look at that picture, the key things we pay attention to certain things is because we like to pay attention to it. Someone will be interested in the house. Other people may be interested to see the track on the road. Other people will wonder what those other the plants involving in it. Other people may even see the fence and the telephone posts, and you see all variety of things. And in psychology, and we call this selective attention. And this is one of the best tools human used for deal with big data. And that is really should also be the fundamental tool today when we come to deal with the big data stored on the computer. And that's the tool. If I could ask, how many people have seen the basketball play video? How many people haven't seen it? The counting basketballs? 1 or 2, 3 people. So just for the benefit of a few people who haven't seen it, then I'll just quickly show you the basketball video. So this particular video asks you to count how many balls being passed around the different players. I can tell you the answer, 15, but you can check whether the 15 pass was correct. And you can see so it's quite difficult to pay attention to the counting process. So when you finish, they ask you how many passes. You work out the task, and then they tell you the 15 passes. And then ask you, say, did you see the gorilla? Particularly for those who never see the video before. For those people who first time saw the video, did you see the gorilla?
No, I did. Yes, I did, but that's because I was told about it in the previous description of the video.
Okay. So in many ways, and that is the question about selective attention. And this usually always been highlighted as the shortcoming of the human vision system because we have so-called changing blindness and so on. But in fact, visually, this is the best tool human has in dealing with the big data. So if you're looking in a more positive way, the selective attention is one of the important features we have. And of course, we have so-called inattentional blindness, as we just see that some people may not see the gorilla and so on. There are other features we have. Gestalt effects, when we always know that in the psychology, I'm not going through detail, is you see the lines, you see the shapes, and so on. And this is also very important effect. We actually associate the semantics with the object. And unfortunately, sometimes you have an illusion as a problem. We also have many visual channels. We don't necessarily see the data just based on the color and the shape. We see the data, the changing, essentially. We see the changing of the objects from their shadows, from illuminance, from a lot of other features involving even the topological features, see whether they're closer, open, and we see all those variations. And some of the visual tasks are parallel. That's why you can see things very quickly. You quickly glance the whole room. You roughly know what is going on. But unfortunately, some of the visual tasks are very sequential. For example, reading text is very slow. You have to read letter by letter, words by words in that particular pattern. And we have a lot of sensors in our eye. We have roughly about 130 million sensors in our eye. But actually, we only have roughly about 1.2 million neural pathways allow us to pass those information to the brain. And in detail, which our color vision is only for roughly about 10,000 points, which deal with the color. So most of our vision actually doesn't deal with the color, and the so-called peripheral vision. So you can see that we have a mechanism. We do taking on a lot of information, but we have a very effective way of process the information to the brain. And by the time the information went to the brain, actually is much, the compression ratio is over 100, kind of 1/100-ish, 1%. And that is very compression ratio in general. And there's a lot of traditional thinking. I noticed one of the colleagues here is interested in working on the virtual environment side. And so the common term is to say those are 3D. And typically you go to the movie theater, you say, let's go to see a 3D movie, and we always talk about 3D. Then there are also so-called 3D devices, which is called a volumetric display, allow you to see, walk around this sort of a globe. You can see the object inside in kind of a 3D. And they have some problems. Some of the glasses may not work and so on. But the one question is always in your mind is, did we really see 3D in compared to this flat screen? And now I present an argument to say, you will agree this is a flat screen, is a 2D. You will also agree if I curve the screen around, it's still 2D. And I curve a little bit more, just extend the lines a little bit more, it's still 2D. You probably agree. But if I turn around to make it a square, it's still 2D. Just means this line extended further. So this, in many ways, is 2D rather than 3D. If I flip it inside out to turn this one inside out, you're looking this one, looking from outside towards inside, this from inside towards outside. It's fundamentally still 2D. In fact, we can't see 3D. And that's very simple. If we can see 3D, we will be able to see our heart. And if anyone really intrigued by that question, there's a well-known book called Flatland, and that particular book was ask everyone to looking from a 2D person's point of view, and what can they see? And if you were a 2D person, so imagine you lower your eye down to the table level, you see everything on the plane, and all you see is just lines, and you don't see the shapes. And as a 3D person, you have an advantage because you stand up high up. Imagine there's a person as a 2D person in here. You can see the 2D person's organs. You can see the person's heart. You can operate on that person without cutting this person open. So if there's a four-dimensional person, they can do it on us. But obviously, we don't have that. So that's the dimensionality issue. But if you think about it, that screen is 2D now, I'm convinced. Now I'm changing the argument a little bit more to say, is that really 2D? It's perhaps not just 2D. So we can see that the black and white, so it's got two-dimensional attributes. We have a space and so on. But if I introduce the grayscale allows encoding an extra dimensional information. So we actually increase the dimensionality in to 3D. We have a color, we have a red, green, RGB, 3 channels, and then we increase the dimension. Then we can have a textures, and we have a letters, which is the additional direction. So we have a numerical letter has its own dimension, and we have alphabetical letters, another dimension, and we have arrows and the shapes and so on. So actually, the flat screen itself is not really 2D. It has many, many more data dimensions, which we call data. So we don't necessarily always need to go to the 3D, which is the device, which is really doesn't give us that much extra dimensionality apart from depth perception. And we can stay on the 2D screen and do a lot of very, very good visualization with it. And so I talk about visual channels. There's a lot of visual channels we can use. We have geometric channels we can use to encode the information. We can encode the information in optical channels such as color, opacity, textures, line styles, shading, shadows. And we can also using topological relationships between objects, connections, which is a channel, and the depth ordering, and those are the channels. We have a lot of very powerful semantic channels such as number, text, symbols, pictogram, and so on. So I'm going to show you some examples of those and how the visualization works. Most of visualization today we use, or most people use, are very, very old. So you're all familiar with the pie chart, but I tell you the pie chart is more than 300 years old. And we all used to use a time series graph. Everyone used time series plot, but I have to say that's more than 1,000 years old. And so you actually are using very, very old technology. And those are the modern visualization technology. Most people probably here haven't even probably heard about it. Power coordinates, very, very powerful visualization tool. Volume rendering for looking into the true 3D objects, such as computer tomography data, which is a stack of images combined together. Video visualization, very similar to summarize a video into a single picture, so you can see the patterns in the video, and which again is a very late sort of a new technology. Tree map is for visualizing the directory structures, which usually takes a lot of space, but condensed into a tree. So those are relatively new technology people actually not quite really familiar with. So there's in our community, there's a particular topic is called visualization literacy. So we will wonder what actually makes it so difficult for people to learn or be aware of the new visualization tech. And there seems to need a kind of a few hundred years to really get people used to it. And that is certainly is at least is a social science issue, or perhaps a psychology in some way, and that is really interesting. And on the other hand, the communication really moving very fast, and we have a lot of older communication and the technologies, we really nowadays don't use them at all. We kind of almost forget them. And we have a lot of new technologies a few hundred years ago coming up, and starting people experiment all the semaphores and telegraphs, and people like my age, we still remember the telegraphs, and the telephones, and all the system. Obviously, those are very old telephones. We don't see them anymore. And obviously coming to the modern, the mobile. Nowadays, the telephone you have is really a computer in some way. And the one phenomenon which is really is where the telephone invented around and sort of just before the last century, and then the Shannon's mathematical theory about communication, the information theory, and the visualization is somewhere roughly just after the telephone being invented. At that time, we have a lot of communication devices. Nobody knows which will work, and so on. And so we're roughly in the era on that, and we're really looking for some theoretical understanding what makes visualization work. And perhaps we shouldn't be really embarrassed, but we actually don't really know why visualization works. We know it kind of works in some cases, but not working in other cases. And in fact, Alexander Bell himself didn't know telephone, how useful telephone could be. So when Bell first invented telephone, he spent all the time traveling around in America. He put the telephone outside the concert hall. He said, if you guys give me money to develop this technology, you can listen to the concert from outside. And that's his selling point. And of course, we don't do that. We don't standing outside the concert hall, have a telephone holding in our hands. And so telephone become a really communication tool. There are other things which we, at that time, we think it's probably not really that useful. So for example, and the chief engineer of the General Post Office to say, we don't need this sort of Yankees devices, and we got, messengers. They can ride bicycles and they can deliver the messages. So similar, occasionally you will see here people to say we don't really need visualization, and all consciously, unconsciously, we say that. So what did Bell say is that when he first time he demonstrated his telephone and to the public in a big demonstration, what he said to the telephone, he said, Mr. Watson, come here, I want to see you. So he's talking to his co-demonstrator in the other room. And that essentially suggests what the real use of the telephone is for communicating the information with others. So if I replace Mr. Watson, you can say the visualization. If Bell had invented the visualization, he would say, Mr. Information, come here, I want to see you. And the question is, what is the information you want to see? And so if you're taking the communication system into account, this is a typical communication. You have a source of the information or data, you encode them in some way, and you're passing through the channel, and you decode them, and then they pass through destination. The visualization pipeline is very similar. You have some data, you do some mapping to the visual signal, and then you pass on to the optical channel to communicate to the receiver. Then we view it. Our perception, our eyes start kicking to make some functions. Then our brain starts working in the cognition. Then you come out to something you're understanding. And you divide them into the three components. So you also have the encode and the channel and the decode. The difference between visualization and the communication is, in communication, as a computer scientist, I have total control of the encode and the decode. I program my encoder, I program and decode. I know exactly how they will work. Here, I can program this part, but I can't program you. You are the viewer, and I have to guess how you would decode it. And that's the challenging part, and that's the interesting part, because it really makes the computer science connect with social science directly, and the psychology and the philosophically, all the thinking in terms of frameworking philosophy will cover both technology, here I can deal with that, which the non-technology part, which we can't deal with that, and that is really exciting. The information actually is not very well defined in the visualization community. We actually don't know what's visualization, what type of information is encoded. So if you look in the literature, all the visualization people always say, oh, visualization gives you insight. The words insight was highlighted here. There's a lot of insight. And if someone say this picture gives you insight, which is you probably will have a little bit doubt in some way. And the insight is deeper understanding. How can a picture give you a deeper understanding? And because it does need your brain to work out the deeper understanding. So I always jokingly say this is the spin of the visualization people, sort of overly amplify how the visualization can do. How does visualization really work? So one of the most effective places where visualization works extremely well is very simple visualization line graph, as you know, is 1,000 years old, are the stockbrokers. Stockbroker watch this line graphs every day, every second, all the time. They watch you see them change it, they have to be. And when they watch the line graph, they have to think a number of things. They have to look at the patterns. They say, are they going up and going down? Are they sort of changing the shape and so on? They compare the pattern against from one company to another company. They see the pattern is common or uncommon and so on. They're looking for clusters. Are they play the same? Are they those, say, foods retailer sector? Are they behave the same way or not? They're also looking for anomaly. If most of retailer sectors they perform in a similar way, but there's one actually is the exception. They're going to ask why and so on. They do all those kind of very, very quick assessment by just simply looking. They don't have time to do statistics. They're just looking at them. And also the visualization offers external memorization. So they don't need to remember it. They don't need to remember this is what I just see. They can always come back. They move your eye backwards, and then you can see that. If you even move last month, they can just move back to the last month to see what's happened. So it's very, very efficient. And they will generate hypotheses when they look into that. They say, the things go up. When simple hypothesis, will they continue to go up? And if it's continue to go up, perhaps I should in some way hold on the share or whatever. I should buy or something like that. If it's possible will go down, then I probably decide sell. And so they have to make this look at the hypothesis. The one thing, they can also evaluate the hypothesis very quickly. And we know how difficult to evaluate the hypothesis. But in this case, you just wait for another hour. If the line goes up, you say, my hypothesis is correct. If the line goes down, you say that my hypothesis is wrong. So it's a very, very economical way for them to do it. They have to. They deal with a huge amount of money every second in that way. Can you do the same thing with spreadsheet? Of course, you will agree with me, they can't. By the way, spreadsheet is more accurate. All the numbers could be 2 decimal points accuracy, while the line graph have no way give you this level of accuracy. Sometimes you will say, will the animation work? So imagine you save the space, you see the lines goes up and down, and you display the prices just on the screen like that, and which is quite dynamic, quite interesting. But if I ask you, say, now, can you decide whether you should buy or sell? And you lost everything. And in psychology, we know human has a very poor temporal memory. People can't remember temporal events easily. So-called the magic 7. You can roughly remember 7, -2, or +2. So between 5 to 9 items when you watch a movie. If I tell you, you spend 10 quids to watch a movie, you only roughly remember 9 items afterwards. And you're probably going to say, okay, someone is going to murder me for that. And so visualization does help you fundamentally to save time. You can do a lot of things much easily with all the selective attention ability, Gestalt Effects, Peripheral Vision search. They allow you to make observation and allow you to omit things you don't really need interesting to see, and you can see the overview. You can external memorization, help you generate the hypothesis, and the pixels can really work very, very effectively. I'm not going to detail on that. They started coming a theory in the sense the visualization can perform like a communication by bundle all the signal into the same signal, and you actually can efficiently deliver it. We know that the multiplexing is a key term in communication, And every our voice speaks through the telephone is mixed with another 1 million voices bundled together and they're being transmitted, then they're decomposed into your telephone afterwards. So there's a very effective way of doing that. And we also, visualization we all know that can help disseminate information quite effectively. Here's just an example. We did some work in Oxford, and the biologists have some videos, which those videos they have really difficult to analyze, and the problem is you can only watch those cells one by one. Every time you can simply just watch one cell, and by the time you work out how this cell behaved, you move to another cell. And so the same video has to be repeatedly watched again, and again. So you have to build a mental model in terms of how they behaved. And we have an Oxford mathematician to say, oh, I can compute a lot of those features. So they compute those cells behaves and to see how they behaved. Then we can display the videos by simply mapping out how the cell moves along the track. So this is a single picture, essentially summarize all the cells in the videos. And now you can see some patterns. Even you watch it, you wouldn't be able to see it. Like the one cell is doing a circular movement around here, it's going round around itself. And the mathematician is particular, or biologist was particularly interesting in how cell seems to have a automatic collision avoidance mechanism. They seem to avoiding each other, but consider they don't have actually really kind of a smart sensor we have. So they're interesting how those behave, come from, and so on. And the cell actually encode, this particular picture encode roughly about 20 dimensions of data, which they call. Obviously, not every time you need to see all the data. It depends on what the biologist's hypothesis. If they are interested in the tail movement, they will focus on that. If they're interested in the shape of the head, apparently some of the cell move like that, just sort of keep sort of moving, jiggling around and that way. So if they're interested in that head shape, then you're looking at that. And if you're looking at the speed and the movement, how efficient they are, you see the three rings, how close to each other, and that indicating is very, very cost effective. That indicating the amount of distance they move, which is actually the single one, the path they follow, which is outside the ring, and the intermediate one, which is the curved approximation. And so you can see we can summarize all those parameters into those cells, and then you can quickly, from a single picture, you can see how the cells from different animals and behaves. And most people, when look at that picture, they're not really, it's too interesting, the human side, but those are the cell dead. And those are the different animals are moving differently. And I normally draw people's attention to look at the rat. So there's the same cell in the rat. And the biologists also put those rats on the drug. So when the rats are on the drug, they move really, really fast. Even faster, they cell faster than the sperm whale, but they're not very efficient. So the gap between the three rings are very wide. So you can just look at the picture, you know they're not moving very well, and they behave quite different. And since the Six Nations is on, and so I'm going to just mention another story. So we worked with the Welsh Rugby Union, and the one nice thing with rugby is they record every single match, not only video, they record in real time into a spreadsheet all the events. You probably wonder how do they do it? Is the computer sort of smart enough to be able to recognize this is scrum, this is sort of foul, and so no, computer can't do it. So they have a very efficient user interface. It's a touch screen. On the touch screen, every single possible event they think could happen have a little button on it. And every play has a number, say number 17, number 18 there. And there's a guy watch the game on the spot and then just simply press the button all the time. And when the halftime comes, they have a gigantic spreadsheet, which obviously gigantic spreadsheet has no use to the coaches. And even you can calculate the statistics, which we see the newspaper always say, oh, you have 45% of a possession, or you have a 55 or sort of a past success and so on. But to the coach, those are statistics. What you can do with that? Does the 45 possession means I need to swap a play, or you can't make a decision? So what we have is we turn this spreadsheet into a line of events visualization. They all have a pictures indicating particular design for coach to indicating those are the events. They can recognize what the events happened and what time, and sometimes they will have a number attached to it. Then we put them on an iPad. And so when the halftime comes, then the coach just take the iPad and started moving around and remind him what actually happened. And he goes to the changing room, starts shouting. So that's sort of the way it works, hugely effective. And if you look in the Six Nations carefully, and if you see the Welsh team, and you will see the Welsh coach team has probably about 3 Apple computers in front of them. And so that's the tools which they have in the process. Okay, we just quickly mentioned that there are different ways of involving people in the visualization. The analysts, the presenters, viewers, they have different relationships, and we still need, from social scientist point of view, and how those relationship works between the analyst and the presenter and the viewers, actually quite complicated. And the scientists are the worst group of people, because they have a conflict of interest. They want to see the visualization, and in order for them to do their research to work out what make observation, but at the same time they also want the visualization to be able for them to show other people to say how great they are, and that usually has a conflict of interest between the two type of visualization you have. So those are a lot of things we are still trying to understand. How can we create a visualization, address different needs, sometimes in conflicts. I'm also working with the International Seismological Center near Reading, and they checking all the earthquake records by reading those gigantic paper sheets every day, 8 hours a day, and to check the record is correct. It takes a lot of time, and we try to help them to improve the speed of the performance. So visualization will save you time if you use correctly, and that's the theme of my talk. Thank you.